כאילו כולכם, you are for statistical mechanics, right? All of you? Okay, so this tutorial is in English, yes?
Yeah.
Okay.
יש עוד תרגול מוקלט?
לא, זה היחיד המוקלט, יש עוד תרגול שקורה בימי שני בשעה 11 או 12, צריך לבדוק.
11.
בימי שלישי ב-4. אוקיי. Technical things. My email. If you have questions or something you want to ask on anything, you can email me. The grade is 67% is final exam. %22 are quizzes. Okay, so you're supposed to have 2 quizzes during the semester, and we are taking the best one of them. And 11% homework.
רגע, זה משהו שהשתנה מהבוקר? כי סטס אמר...
מה סטס אמר הבוקר?
שיש בוחן אחד ביחד שבוע שמונים. כמו הרבה החלטים לקבל.
אוקיי. So quiz. Okay, so today we will repeat on thermodynamics, especially on how to pick the equations we want to work with to solve specific exercise. Okay, so we're starting with the laws of thermodynamics. So first law of thermodynamics. So the first law says that the total energy of a system is composed from heat, plus available energy for work. Okay, so from our side we have some energy we can use to do work, and we have energy we cannot use to do work. Okay, heat and available energy. And we write it as the change in the total energy in the system equals to the heat that the process creates, okay, a heat that creates in the system, minus the work the system have done, the available energy we used in this process. Okay. The second law of thermodynamics. Okay, so the second law says that in a closed system, meaning in a system that we don't insert energy from outside of the system. So we have a closed system, and in such a system, the available energy can only decrease or stay or remain the same, but it cannot be increased. Okay? Okay, now pay attention that this is only for closed system. So if we can affect the system from outside, we can always insert available energy. Okay, but in a closed system, we cannot. So let's write it as how we write it in mathematical way. So to write it as equation, we are defining a new variable. We called it. We write it as S, and it's called the entropy of the system. And it defined as ds equals to delta q over t, and then we can write the second law of thermodynamics as delta s is always bigger or equal to 0. Okay, so the available energy decreases and the entropy can only increase or stay the same. This definition is valid for quasi-static process. You remember what is quasi-static process?
שאפשר לחזור.
Okay, so let's define it. So it's actually some theoretical idea where we're saying
You mean that is not so fast?
yeah, so we have some a process, yes, that has a beginning point and some end point, and the actual process can look like something like this. Something happened between those two dots. But when we're talking about quasi-static process, we say, okay, let's assume that the process occurs very, very slowly. Okay, so at each point in the process, the system is in equilibrium. Okay, so we're saying the process is always equilibrium of the system, and then we can use equations that are valid for equilibrium. Okay, why we can use it? So we can use it if we only care for the start and ending point. Okay, if we don't care what the process between them, but we only want to know what happened in the end point relative to the start point. Okay, so we can assume that the process is always in equilibrium, and then the results we get in won't be valid for the real process along the way, but it will be valid for the initial and the final point. Okay, so if we will back to the second law of thermodynamics, so we defined the entropy, we defined the quasi-static process, and this is the mathematical second law. So now we can say that if we have a process that occurs, that goes from A to B in closed system, so we can see that sometimes we will see a question in a closed system, but sometimes we will see that the question tells us that we have an adiabatic process. So it's the same because adiabatic tells us that there is no heat transfer from the system or into the system. So it's actually a closed system. There is no energy exchange. So if we have a process from A to B, we can say that the entropy of state B is bigger or equal to the entropy of state A. And then we can divide it into two different processes. So if SB is bigger than SA, we can say that the process is not reversible. Okay, so we can go from A to B, but we cannot go back from B to A, because then the entropy will decrease. So this is irreversible process. And we have the second type, that's SB equals to SA. And then the process is reversible because we can go back from B to A because the entropy don't decrease.
And both of them can be quasi-static processes?
Yeah, so quasi-static process is only theoretical idea. Okay, it's just that we can use equation that of equilibrium.
So it can be irreversible.
Yeah. Okay. So now we want to take those two laws of thermodynamics, and we want to get some actual mathematical terms that we can work with. Okay, so the first one Okay, so the first one, we want an equation for quasi-static process. And it describes the differential of the energy of the system. So du equals to TdS minus P dV. Okay, so we have here from the first law of thermodynamics. So this is what we call the heat, and we use the definition of the entropy to write it like this. And this is the work. Okay, if we have another types of work, like in a rubber, if we have a tension, so we will have here other terms of work. Okay, and then we have lots of different energy definitions that arise from mathematical transitions. So we have from some transformations. We don't care what transformations, but we have the free energy of Helmholtz. So we write it as F, and its variables are the temperature and the volume, equals to U minus Ts, and its differential dF equals to minus S dt minus pdv. We have the enthalpy. So age and its variable are S and P, equals to U plus PV, and its differential is TdS plus VdP. And the last one is free energy of Gibbs. So G Tp equals to H minus Ts, and its differential equals to Tds minus SDT plus VdP. So all those terms are energy terms. In equilibrium, all those terms are at minimum point. Okay, and when we solve a question, so we don't need to use all the energy terms. Okay, we need only one to describe the energy of the system, and we're choosing the one that suits us for the changing variables. Okay, so if we have a system that describe using the temperature and the volume, we will use the free energy of Helmholtz. But if we have a question that describe a system using the entropy and the pressure, we will use the enthalpy. Okay, so it depends the variables of the system.
And then every one of them is the energy?
Yes.
It's different shorter, but it's the same.
So all the terms are describing the energy, but each one describe it using different variables. Okay, we also have Maxwell's relations. So we have here 4 other equations that connect between derivatives. So we have partial derivative of the temperature relative to the volume, where the entropy is constant, equals to minus dP to ds, when the volume is constant, equals to second derivative of u to s and v. Okay, so all those derivatives you have on the model, okay, in the paper on the model, where P is constant, and this is from the enthalpy. We have derivative of S relative to V, where T is constant, equals to derivative of P to T, where V is constant, and this is from the free energy of Helmholtz. And the last one is minus ds to dp equals to dv dt with p constant equals to second derivative of g to t and p. Okay. Last thing we want to define is equation of state. So equation of state is some equation that describe the system using only the variables of the system. Any variable of the system, but only the variable of the system. Okay? So it can be the pressure, the volume, the energy, but not some outside variables. Okay. So we have now an example. Okay, so we have a elastic rubber with length L, temperature T, and tension G. It is known that we have some function that's defined by the derivative of J over T, where L is constant, and that equals to some constant A, L divided by L0, 1 minus L0 to L third. And we have another function F that's defined by the derivative of J where T is constant equals to AT divided by L0, 1 plus 2 L0 to L in the third. Okay, and L0 is the length of the rubber in the relaxed state, and A is some constant. Okay, so those are the equations in the question, and now we are asked to find the equation of state. Okay, so we want some equation that depends only the variables of the system. Okay, so we have here equations with the variable of the system, but we have here also derivatives, and we don't want it. Okay, we want only the variable of the system. Okay. Some experimental functions given in the question. Okay, so first let's see what are the variables of the question. Okay, so we're given here a variable L, the length of the rubber, we have here the temperature of the system, and we have the tension of the rubber. Okay, so we want some equation that with those variables. And what we have for now are those two equations. So we see here we have the derivative of j relative to t and the derivative of j relative to L. So we can integrate on both equations and find the dependence of j on the other variables of the system. Okay, so let's integrate and start with g. Okay, so the function g that has dependence only on L and not on t equals to the derivative of j relative to t where L is constant. Okay, so we can write that g dt equals to dj, but we need to remember that all what we're doing here is with the assumption that L is constant. So the integration is relatively easy here because g depends only on L and L is constant for us now. So all we need to do is take this function and just multiply it by t. So we're getting that j that depends on t and L equals to the function g times t, and we have here we need to add here a constant. Okay, so still we need to remember that L is constant for us now, so the constant we're adding here can be with dependence on L because L is constant. Okay, and if we are now doing here derivative relative to t, this is drops out and we are getting this equation. Okay, so one function of j. Now let's do it for f. So again, we have f dl equals to dj. So here the integration is a bit more complex, but we can do it. So so we're getting that j that depends on t and L equals, in the final solution, again the function g times t, and again we're adding here a constant, and now this constant can have dependence on t because here t is constant. Okay, so we have two functions of j, and so we can find this constant. So this j should be equals to this j. Okay, so gt and gt are equals. Okay, so actually those constants should be equal one to another. Okay, what can we learn from here? So we know C1 can be dependent on L and C2 can be dependent on T. Okay, but C1 cannot be dependent on T. So it means that in order for those constants to be equal, they are both just some constant that has no dependence not on L and not on T.
I didn't understand the second equation of G.
From here to here.
Yes.
So,
Why?
yeah.
Why didn't you integrate F?
So we integrated F. Okay. We integrated F according to L.
Okay.
And we did this integration and we just got the function G times T.
Okay. This is the.
Yes.
Okay.
The
After
final
the-
solution. Yes, yes. Okay. So we have JTL equals to the function G times T plus some constant. And what is this constant? So we need to go back to the question and see what other thing we know on the system. Okay, so we know that we have this value, L0, that is the length of the rubber in the relaxed state, meaning when J equals to 0, when there is no tension, the length of the rubber is L0, meaning JT L0 equals to 0. Okay, let's insert it into here. So we're getting that G L0 times T plus C. So this is equals to 0. We're getting here only C, and this is. Oh, sorry. Yeah, okay.
G of L0 is 0.
Yeah, so this is equals, this is 0, so this is just equals to C, and this is should be 0, so our constant equals to 0. So our final equations of state J equals to the function GL times T. Okay, and we can also write it, and this is, I'm doing it because we will need it on the next question. So J, we can write it as equals to T, derivative of J according to T, where L is constant. This is by the definition of the G function. Okay, right? The G function equals to something with L, and by definition it equals to the derivative of J by T. Great. Okay, so this is an example for equation of state. And now I want, in general, to see. In this case, we usually will have another questions in this one. So equation of state is usually only step 1. So now we want to see which equation in general we can use in this question. Okay. So first of all,
we wanted דווקא the המשוואה to be like this, כאילו with derivative, or
So it's another way to describe the equation of state. It's just another equation that we can use. Okay? So I write it in many ways that I can, and just so I can use any help I can get. Okay, so available equations. First of all, we are always using the assumption of quasi-static process. Okay, that means that we always can use these equations. du equals to TdS minus PdV. But here we have a rubber, we don't have volume or P, so we are writing this equation in this case with the length and the tension. So here we will write it as TdS plus JdL. So P goes to minus J, or minus P goes to plus J, and V goes to L.
Why the plus?
Huh?
Why the plus?
Because the direction of the work done on the system, or the system done on the surroundings.
Okay.
Okay. Second equation, we will pick the equation of the energy we want to use. Okay, so first is always the quasi-static equation. Second is another energy equation, or Helmholtz, or Gibbs, or the enthalpy. Okay, so here our variables are T, J, and L. Okay, or P and V, yeah. So the energy equation we pick here will be the free Helmholtz energy, okay? Because the variable of the free Helmholtz energy are T and L, okay? So those are variables of the system, so we will pick this energy. Okay, and we usually don't work with F as energy, but with its differential. So dF equals to minus S dt plus J dF. Okay, after we are picking energy equation,
Put it with the Gibbs.
what are the variables of Gibbs? Yeah, so we can use Gibbs also. Okay, after we're picking energy equation, we want to take the relative Maxwell relations. Okay, so Maxwell relations, we had the second derivative of something. Okay, so if we picked F here, we will take the Maxwell relations with the second derivative of F. So in this case, we have second derivative of F minus relative to T and L equals to dou S to dou V. T equals to dP to dt. Okay, then we can take equations we have in the question. So in this case, we have the equation of state, right? We found the equation of state. So we have those more two equations, this one and this one, that we can use. And then if we have other equations in the question, like if they are saying that the process is reversible. Okay, so if the process is reversible, we can use delta S equals to 0. Okay, so first we're taking those
זה לא
first
מכבד,
three.
לא?
חכו, תנו לנו לסיים ואז תיכנסו. אוקיי, so first we're taking always. לא נסיים עדיין. לא, עדיין לא, אנחנו עדיין באמצע שיעור.
מתי תסיים?
פשוט עוד 2 דקות. עוד 2 דקות, תחכו שנסיים. Okay, so we always start with those 3 equations, and then we'll see if we have equation of state, and then we're going to the question with the question and see if we can get from there any other equation. Okay, any questions? Okay, so exercise will be on Moodle tomorrow. Okay, any questions? Just email to me.
תרגיל הבית נבדקים?
סתם. תרגל הבית נבדקים על הגשה סבירה. כלומר, שכל השאלות הוגשו, שכל שאלה אשכרה מתייחסת, כאילו, כל תשובה אשכרה מתייחסת לשאלה. לא אכפת לנו עם התשובה הסופית. כאילו, אנחנו רוצים לראות שהייתה עבודה. זה
מה?
דיוורק שווה שונה
זה החום.
צריך, לא יודע.
אז שאר התרגולים זה רק פרונטלי וזה פתאום מוקלט.
נכון. שאר התרגולים בעברית גם.
כן, בסדר. זה מה שזה אומר. תודה.